Hi everyone, welcome back to my channel. In this video series, we are targeting in learning how we can implement and train different kind of neural networks making use of Keras. And from the previous videos, you may have seen that instead of just focusing on the model, we go for a full-fledged end-to-end project, right? So far we have covered ANNs, like the fully connected models, fully connected layer containing models. We have covered CNNs, convolution neural networks. So we have covered RNNs. So basically we deal with the LSTM. So in case of GRU, the things are only going to exactly be the same. We are just going to replace the word LSTM with GRU, right? But okay, now these like are the three kind of deep learning models we have for classification or even regression kind of problems. The next thing is a bit complex. That is a combination of CNNs and RNNs, right? So it is very much possible that you develop a model, excuse me, which make use of both kind of layers. It has CNN layers, it has RNN layers, and moreover, like for the application of simple application is image captioning, right? For image captioning, what we do is, right, what we have is we have CNN part of the model which processes the visual part of the image, and we have the LSTM part of the model which do that NLP kind of a work. Like this is kind of an example, right? Same is the case with this one, right? So so the question is how we are going to implement that, right? So as my strategy is to do an end-to-end project, I come up with a video, right? In this video we are going to develop a very strange kind of model in which we are going to have bidirectional GRU layers in the beginning of the model, and then we are going to have CNN layers following the bidirectional GRU part. So I have shown you some strange models which have CNNs then LSTMs layers, but what if even the case is opposite to that, right? So the code which I'm going to present in this video is from one of my papers. It's named UltaNet. It's available on IEEE Explorer. So this is the model which we are going to implement. And this is for human activity recognition data. I have shown you the in one of the videos, in the case of LSTMs, RNNs, we have made use of sequential data of accelerometers of a smartphone. So the same data set we are going to use in this video, and we are going to develop this kind of a model. So what we do is here is that we have bidirectional GRU layers, and there are 64 bidirectional GRU units. Then we apply the batch normalization, and the feature set generated by that bidirectional GRU model is then given to different kind of CNN kernels, right, for convolutions. So we apply 1 cross 1 convolution, and then we apply 1 cross 3 convolution. Then and we also give that to 1 cross 1, and then we apply 1 cross 5. Same is going with 1 cross 1 and then 1 cross 7. And we also apply 1 cross 1, and we also apply max pool, and then we apply 1 cross 1, and then we concatenate all the feature sets generated at this point. After that we apply the dropout, then we apply 1 cross 1 convolutions again, 8 of them. Then we apply 1 cross 1 convolutions again, 6 of them. Then we don't have any fully connected layer, we apply global average pooling, and then we do the classification, right? So from learner's perspective, this is a very strange model, right? I recently published it, and it does very good for the smartphone data for activity recognition. The good thing is it doesn't have any fully connected layer as well. So as the model is very unique, I named it Ulta. Ulta means it's a Urdu term that means opposite or antithesis, right? So let's implement an antithesis model, right? The code is going to be shared with you. The link of this notebook is going to be present in the description of the video, right? So the upper portion of the code is exactly the same to that of the LSTM video, right? So I directly come to the model part, right? Okay, so here we come to the model part. So this is the function its name is inception underscore network. So it's just a name, you can give it any name, create model or anything. Then here the main thing starts. Okay, like the LSTM video, the LSTM model, we first get the input feature size. So basically the size of the segment which is going to be input to this model, right? So for that, okay, one good thing, we cannot make use of sequential library of Keras here, right? Because in case of sequential library, all you can do is you can have concatenated set of basically one after another kind of models, right? You cannot create models which take various inputs and do the processing in parallel and then they combine the output, right? So that's another learning point in this. Okay, so we need to include a layer that's called input, okay, to create the layer that handles the incoming signals. Okay, for that you import input from one of the layers. So Keras dot layer, from Keras dot layer we are going to import input. It has been imported here, right? Okay, so the way we write the code to such kind of cases is that you on the right hand side you write the input, on the left hand side you get the output in some variable and pass that variable as an input to the next layer. Okay, so input layer is getting the input shape and I'm just giving it a name. So by the way, for any layer of a model made in Keras, you can give it a unique name. Okay, and this is an optional parameter, you may give it or you may not give it. It's a good practice to do that, so therefore you are finding it here, but it's totally unnecessary. Okay. Okay, so the input signal is now the output of the input layer and that is given to the first layer, that is the bidirectional GRU layer. Okay, so from layers I have imported bidirectional and I have imported GRU. Okay, so basically it's a layer inside a layer. We have GRU layer which has 64 units and its return sequence is set to true, and that layer is being given to bidirectional. Okay, so you may have LSTM here, right? So the overall layer becomes this, and the input signal is then given to this, right? The output of this is generated, and I call it GRU1, and that GRU1 is given as an input layer to bidirectional, batch normalization layer. Okay, so we have the batch normalization here. Okay, now after the feature set generated at this point, we are giving this input as input to all these kernels and applying max pool as well, right? So one directional convolution layer, interesting, right? We have two kind of convolution layers in Keras. One is the two-dimensional convolution layers which you have seen in CNN video, right? But you may have a data that is not bidirectional, that is like in the case of signals you have 1D data, right? So for the handling 1D data we have dedicated one-dimensional convolution layers. Okay, it is possible that we convert the 1D data into 2D data and then use 2D convolutions on that, but anyhow, if you have the facility, you can directly use that. Okay, so I'm not reshaping my data. So I imported 1D convolution layer from convolution layers of Keras. From Keras.layers.convolution I imported 1D, right? And then I'm telling it how many kernels, how many filters I want to have in this layer, and that is 10. Okay, in my case all of these are 10. My target was to come up with a very less shallow kind of a model, so the numbers of the kernels were kept low. But there was a lot of research, lot of experimentation involved in selecting each and every layer of this model. Okay, so we set it to 10. Then the kernel size, right? The first kernels I'm applying here are 1 cross 1. Okay, and the kernel size is set to 1. Padding is set to same. If you're not going to set it, it's going to be automatically same. Okay, then I tell it the activation to be reload. Okay, the good thing is you have been looking in my previous videos, I'm applying a separate layer of activation and then I'm telling that to be of reload or anything else. But the good thing is if you want to directly apply activation to the output of any layer, you can directly do it inside the layer. Okay, you don't need to have a separate activation layer, although I have imported it, but I'm not going for that. Okay, I think something wrong has happened. No, yeah. Okay, so next thing is optional. I'm giving it a name. Okay, so the output of this 1x1 convolution is then given as an input to 1x3 convolution layer. The syntax is exactly the same, only the kernel size is 3. Same thing is happening at here. We have the convolution size of 5 and 7 here. Okay, then this is the direct 1x1 convolution layer. We are having 1x1 convolution which is getting bn input. Okay, talking about the max pool, first I'm applying the max pool. Again, max pool can also be 1D, because if so, Keras has a full-fledged package for doing convolutions on 1D kind of data, right? On signals specifically. So like we have 2D max pool, we have 1D max pool. So we imported from convolution layers package, we import max pooling 1D. Okay, and we are setting the pool size to 1, right? Padding is set to same. Then I apply 1x1 convolution to the output of this. And once the spatial dimensions of all of these are same, I am concatenating that. The feature sets generated by all these layers. Okay. I'm at this point right now. Okay. So for that, we have a layer called concatenate. The way to use it is you can go for importing it like from keras.layers import concatenate, or you can directly import it like this. Okay, because I was not referring to it again and again, I haven't imported it previously. So in this, you are telling it that concatenate all the feature sets in access to, means one after another. So if you have seen Inception Net, you will be familiar with concatenation of the features. Okay, yeah, this is something similar to that. So this is right. You have the previous layer, you're generating the output from different kernels, and then you're concatenating that. Same is the case it is here. Okay. Okay. After that, I'm applying dropout. Okay, so the output generated here is mid 1A, and I'm giving that as an input to a dropout of 0.5. Right, we are at this point. Then I'm applying 8 1x1 kernels, and after that I'm applying 6 1x1 kernels, and then I'm applying global average pooling. Okay, global average pooling is also very interesting thing. So what you do is you do the average pooling, you average the things in the kernel, and then you get one output. Okay, right. And the good thing is this is again the idea is taken from computer vision. So you have 1D layers as well, you have 2D layers as well. So if you apply global average pooling to one kernel, you are going to get one output of from that entire kernel. So basically that's an average of it, right? This is it. So you get average of all this. So in the case we had 6 kernels at this point, we are going to get exactly 6 outputs. And then I apply a dense layer of softmax for prediction, right? And the input is given to this layer, right? And in the dense layer, I'm telling it the output size, which I'm getting from the shape of the training data. So that is it, right? Here is the summary, right? Here is the training going on. I did the training on 80 epochs. I have changed the variable to, I guess, 10. So when you're going to run, it's going to run for 10. You may change it to 80 to reproduce the results, right? Here we can see that the model is not overfitting, right? Accuracy is 97%. I have plotted the model to check whether everything is connected properly or not. Then we have the confusion matrix and the performance report. You may ignore this ROC curve for the time being. So that is it. So in this video, we have learned how to make a strange kind of model in Keras. Okay, do leave your confusions and problems or whatever things you face, whatever difficulties you face in the comment box. I will try my best to answer you as soon as possible. and do give me your feedback and let me know what you exactly want me to discuss on this channel. Till then, thank you very much. Take care.